So it's now my pleasure to introduce Filip. So I heard from Abstract that they have started building a programming language with effect handlers in it. And I'm quite excited about that because Poland, in part thanks to Filip, is one of the nice places to have people design a programming language with effect handlers and proofs about what it does right now. So at least I'm eager to hear more about it.
So, thanks Gabriel. It's like all the cool kids are doing it, so we want to do it on it too. So it's very much a work in progress, but I felt that it would be nice to give a short talk about what we're doing with algebraic effects and handlers, or like someone could call it effect handlers, because really most of these languages don't like sort of this happening, right? So, it's probably going to raise more questions than answers, which I think is okay for an audience like that, right? So, algebraic effects and handlers are this sort of new and very promising, I think, way or approach to languages for various reasons. So first of all, we get pure fragment of the language that is actually pure. And this is like incredibly cool. This is what the Haskell people have been telling us and all programmers for decades, right? Purity is cool. Pure programs, more transformations, more equivalences, easier reasoning, and we get a fragment of a language that can do exactly that, right? On the other hand, what we can do is we can write effectful code without much syntactic overhead. So, we can do one up on the Haskell guys too. Yeah. And it's not the built-in effects, because, Python effect systems which would allow us to have both the pure fragment and effectful code without static overhead, they've been around for 2 decades, right? It's what, late 80s, second half of the 80s, since when the original papers by Lucas and Gilbert were written. So what we gain by having a language with effect handlers is the fact that we can easily define custom effects and still retain both of the other benefits. So in a way, it combines the best features of Haskell and ML. And really, it gives us a little bit more than that. Because in a way, and this is a way that's being made precise at ICFP last year by Ohag and Sam and their co-authors, this is really a way of writing programs with effect handlers is really a way of using the limited continuations. And I've been working with the limited continuations for a while now, and this is the only way of writing programs with delimited continuations that doesn't make your head explode. It's a way that actually allows us to get some reasonable reasoning principles, and we've written on that with my co-authors in Wrocław, and it's like the list of features really gives you, if we can get that together, this is going to be a really, really nice way to program. And of course, a lot of people have thought just the same, right? So there's a lot of languages that jump on this bandwagon, and some of these are new languages like Def and Copper and Frank and Edinburgh, and some of them are extensions of existing languages like Idris and Blink, and I think there's efforts to add effects to Haskell and multi-Perot camel, and I probably forgot some in this list. So, like Gabriel said, yes, we wanted in on it, and written another very, very highly experimental language that's tentatively called Helium. So all of these implementations are highly experimental. Ours is even more experimental. Oh, and by the way, if you want to ask questions during the talk, please do.
Let me be pedantic. I think Poca does not really qualify as a new language in the sense that Dan had been playing with ways to do effect typing for a few years before he started adding language.
Yes. And I think it's sort of a little bit less sort of more grown up and less experimental than F and France.
It's a bit too usable
to be. You're right. Yes.
Can I be more pedantic and say that links has an S on the end?
I'm sorry, I always do one way and the other. Sorry about that. Okay, so for those of you who haven't jumped on the effect handlers bandwagon yet, let me just give you a small taster, and then we'll go on to the main matter of the talk and try to think about how to combine effects and another feature that ML is well known for, which is modular abstraction. So first off, like I said, we can define effects in a language, local custom effects. In this case, this is an effect reader, which is very similar to well-known Haskell monad called reader, of which we can, and this effect has one operation, operation ask, which takes a unit as an argument and gives us back a type A, right? And this effect in itself is just a piece of specification. So when we write ask unit in a program, it doesn't do anything of its own, right? So what it does is it dynamically looks up a handler for this effect. And one particular handler that could be provided for this reader is, well, this little bit of code here, which when an operation ask is called and ask looks up this particular effect, it gives back 42, right? But like I said, effects can do much more than this. In particular, they give us control flow operations. So basically, they allow us to do things to the control flow. In particular, we can write an effect like this, which is an error. So we can raise with a parameter that's there as a parameter of the error effect, and we get back something, anything, which basically means that the handler cannot provide any value of this type, right? And this means that the handler cannot resume, like the handler for the reader did. It cannot give back to the call site, to the place that asked for the value. It cannot give back a 42 or anything else, because this is universal quantified time. So this is basically for all x's. It's an empty time. But what we can do is we can check whether an error was raised, right? So if an error was raised, we return true, and if an error wasn't raised, we return false. So in a way, these effect handlers are simply generalizations in a very, very strong way of standard handlers for exceptions, right? These two guys look just like any other exception in a language with exceptions. So if an error was raised, we take this path. The control basically goes through the control stack, finds the place where the handler was located, discards the entire stack, and returns true. In the other case, we simply return false. So these are two very simple effects. And and of course we want to type check programs that use them. Yeah. Sorry.
Yeah, did you mean to call that error, or was it supposed to be raised?
It should be raised, that's fine. Right. Yeah, that should be the same name as here, just like here we have asked the same operation that we declared in the name. Okay, here it's called raise, like it should. Right, so here we have a small chunk of code. If ask is equal to 42, then raise, otherwise return pi. Right? So we have two effects, and in contrast to the monadic approach, it's very easy to mix various effects together. So this is one of the big selling points in terms of programming of these algebraic effects. It's that, you know, we can type this whole expression as an integer given these two constraints, right? So the reader should better return an integer when asked, and the error should better wish for a unit to be given to it. And since the error exception, the raise operation could produce any type, as a result, it can in particular provide us with an integer. Right? No problem. So, the usual type systems for these languages with algebraic effects are really type and effect systems, which give us both information about the return type of the program and information about over approximation of the information of what effects can be used by the program. Right? In this case, in one of the possible paths, error would not be raised, but still the entire program has the effect that contains both error and reader. Okay. Now, the thing is, if we want to talk about abstraction, then the usual problems appear. It's very difficult to talk about abstractions on small code fragments because, well, if you have a very small program, then it's hard to justify why we should care about abstraction and why we should build, you know, huge stacks of modules and whatever in order to build the abstraction. On the other hand, if we use too big a program, then it's hardly possible to you know, fit it in your mind in a confined time of a talk. So what we found was that a sensible, we think, example that demonstrates the need for abstraction is unification. And this here, don't try to read this. This is a pseudocode from a review paper on unification that describes a unification algorithm that uses a unified data structure. So it's sort of nice, efficient implementation of the unification, first order unification, on two terms that uses union find in order not to try to unify subterms more than once. So the standard pure Robinson's algorithm generally has a problem with trying to, where it can be made to unify the same subterms more than once. And this algorithm, originally due to Jacques does not do that. And we'll try to work our way to encode this algorithm in a nice way in a language with algebraic effects and handlers. So what is the first thing we need, first ingredient that we need in order to encode this algorithm? Well, we need a unified data structure, or a disjoint set data structure. And a standard ML, SML, or OCaml interface for a unified data structure would look roughly like this, right? Modular syntax. So we have a type constructor of disjoint sets, and the idea is that this type carries with it a representative. So it's not the union find of algorithms textbooks that's encoded on an array, and the indexing to array tells you whether it's a root or not. It's a more abstract representation where we have a type of representatives, which makes it very nice if we want to encode things like I don't know, a type system for a simply type lambda calculus that would use a unification algorithm based on top of this. Right? So what we have here are three operations. One for creating a new disjoint set that contains only its chosen representative. One that finds a representative based on given a set, and one that unites two sets. Right? And if we want to unite two sets, we'd better find a way, or provide a way, to unite the representatives. So what we have here is a function that tells us how to do it. Right? Now, if we think of a language where the standard arrow is pure, then it should be clear that this specification is not particularly useful. Right? What the union does in the end is return a union. If this function space is pure, there's not particularly many outcomes that would be useful. Right? So clearly, if we want a specification that where this arrow is pure, then we have to extend it somehow. And one way we could conceivably do this is by turning the whole thing into an effect. So rather than provide an implementation as such of this signature, we could say, well, mu is an operation, and find is an operation, and union is an operation. Right? And this would lead to a specification like this, where we have some type constructor of sets, and we have an effect, and whenever we call mu or find or union, the control just goes back up to the effect handler, which implements the actual union find operations. All right? So basically, different handlers for this effect would provide different implementations of the union find data structure. Now, this is enough to implement simple union find based algorithms. So for instance, if we had a representation of graphs where the representatives we picked here would be something simple like integers, and we wouldn't really care which one we picked here, that would be perfectly doable using this interface. But the union operation still poses a problem, because this closure here, this function, is still pure. This function space that tells us what happens when we unify two representatives of two disjoint sets is a pure function space. So we cannot provide a function that has some side effects. Now, if we were to read through that complex pseudocode that we've seen a couple slides ago about how the unification algorithm works, we'd see that in the case where we have two function symbols that we are trying to unite, what we do is we add to a word list all the subtrees, all the pairs of subtrees, so that they can be processed. And so in effect, what happens is we provide a function that is effective in this place. In the union, we call a function that is effective. Okay, we could annotate this place here with an effect, and what that would require us is to annotate the entire union find, parameterize the union find slightly more with an effect type parameter, which is doable. The problem is this would not lead us in the direction that we need to go, because this closure could only be called in the handler, which means it would be called in a way too far down the stack of effect handlers, which is a thing that if you are used to programming with effect handlers, it matters a lot. It matters a lot which order the effect handlers are composed in. And in this case, it so happens that it's very important that the function for the union gets called in the place at the call site of the union, rather than in the effect function. And we'll see why in a minute. So, it's a specification, but it doesn't quite cut it. We need something more. And so, what we propose in this case is to extend the sorts of signatures for modules that we can write in a method. So we add another type constructor, or rather effect constructor. So we say we have an abstract type of sets and an abstract effect UF, which we don't know what it is. And now we can freely allocate these arrows with a UF, and this arrow, we can say, it does not only the effect UF, but also whatever this arrow wanted to do. Right? So we add a UFA and an E here. Yes?
E is polymorphic variable.
E is polymorphic, just like A is polymorphic. Yes, so small, lowercase letters here are type variables in a sort of Haskell style. All right. So now there is one issue still with this specification. Is it clear what it is? Well, we can definitely introduce the effect UF into our typing derivation. We have no way to remove it. Normally, we remove an effect like UF from a typing derivation by a handler. But the handler has to provide implementation for all the operations. What operations? It's an abstract effect. So what we can do is provide an abstract effect handler, which is a thing that's typed roughly in this way, right? It removes a UF effect from an arrow and leaves everything else in place, and doesn't do anything to the problem. So this is the thing that actually implements most of the union type algorithm, except for the fact that union cannot be a simple operation, but also has to do some work. Right? And as usual with abstract types and abstract effects, the actual implementation of union type is not particularly interesting. What is interesting is how we can use it. So in order to encode the entire unification algorithm, we have to walk through some preliminaries. So what do we have to assume? Well, first off, what is a term? Well, a term is, let's just take any signature and build a term with some variables over it. Some good stuff. And let's assume that the signature has a fmap in zip width associated with it. So fmap basically just allows us to map under the term constructors, under the function symbols, and note that these functions are annotated with an effect. So these functions that allow us to map over function symbols can be affected, which is nice. And zip width, additionally, can raise an error. When should zip width raise an error? Come again?
When the inputs are not of the same size?
Well, are different, size has nothing to do with it. These are just different function symbols, right? I mean, they might have the same parity, but, one be plus and the other minus, right? So basically, yes, when we try to apply zip width to two different function constructors, we'll raise an error. And this is important because this is the source of failure in the unification algorithm, ultimately. Okay? And we need a couple extra effects in order to express the unification nicely. And one of these is writer, which allows us to tell things. It's an inverse of a reader, right? Just like with monads. And we'll have a handler for the writer that is basically a word list. So it processes things round and round and round until it runs out of things to process. When it runs out of things to process, it means things have unified entirely. And we'll also build an association list using a effect so that we can abstract from the gory details of looking things up in a list. And then we can actually write a fully working implementation of unification in a sort of, well, it's a little bit more than a slide if we run over top and bottom, right? So what happens here? Let's just run through this reasonably quickly. So we have to build a representation of unification terms, which are terms that can contain, well, that do contain these disjoint sets that describe, the unification variables. These are just the unification variables taken abstractly. And then we need a couple of additional functions. So first off, when we get to trees, we need to convert the representation to one built of unification variables. This is what the first function does. If it sees a variable, it just looks through an association list to find the appropriate set. If it finds one, this is the one. If not, it should allocate a fresh one, which is what the modular does. In the case where we have a function symbol, we simply recurse under the function symbol and rebuild the thing. And as you can see, under the U-term, under the F-map there's a function walk_tree, which clearly is effectful. Right? So this is reasonably important because, well, like I said before, it's important that the F-map and zip_width functions can be effectful. Right? So this is the first ingredient, and if we look down here at the definition of unify, what happens first is we convert both T1 and T2 into a representation that is basically just a unification variable, or pair of unification variables. So what happens next? Well, we tell. We call the tell operation from the right hand. So we add this pair of trees to a word list. And what happens next is this is an effectful operation, right? What can it do? It definitely does the writer operation, because the writer effect is the one for which tell is an operation. So this is the first thing, or one of the things that it does, and the other is all the operations that walk_tree can cause, or all the effects that walk_tree can cause, these being ASOP and union find. So we have three effects down here: the association list, the work list or writer, and the union find. And what we see here is three handlers. For association list, which is not particularly interesting, for a work list, which requires us to give it the way of handling each of the elements of the work list, and the abstract handler for union find. So the only thing that's left is, well, learning what the function that is used to process the pairs of trees does. And what it should do is basically call union, which is what happens here under some boilerplate unfolding. Okay, but as we remember, union required this function that tells us how to unite the two elements, right? The two representatives. And this is what happens here in this middle part of the slide. And what happens is, well, if one of these two is a variable, a unification variable, then we should simply pick the other one. Nothing to see here. However, in the other case, it doesn't really matter which we pick, as long as the subtrees are unifiable. So we have a function for that, right? Zip_width. Zip_width should get something to unite the subtrees. What should it be? Well, a function that picks whichever, in this case A, and adds the pair of two subtrees back into the word list. So basically what happens is we hit the two subtrees, try to check whether they are the same constructors. If they are the same constructors, then add all the children pairwise back into the word queue. Okay. So how does this compare to the pseudocode? I mean, there's details, right? You have to actually go through the code in more detail to fully understand it. But how does this compare to the algorithm? I mean, okay, this thing here is way more detailed. In particular, it contains all the pseudocodes for the word list operations and all the pseudocodes for zip width, which will be listed here. But on balance, it's roughly the same size. So I believe that even a reasonably complex bit of code like unification, if it can fit this sort of size, it's probably not too bad. So okay, like this is not particularly strong argument for abstraction on its own, probably. And it's just a piece of code. It's nice that you can write an algorithm like that, but how well does it scale? And the answer is we're not entirely certain. We have scaled it up in the sense that we have given unification itself an abstract interface and then used it to build things like type systems, simple type systems that were using the unification as a black box. But it's early days. There's a lot more coding to be done. What I think this shows is that the abstract effects play a certain role in this whole spectrum of effects and handlers. In particular, when they appeared, was when we needed to control the call site of the function, when we needed something that would, in the end, have more effects than just the one we were thinking of, in this case union find, right? The union had to have a richer effect specification as a result. They do allow to limit the client's handling of library effects, and this is very important from a point of view of like relational reasoning and similar aspects, which is what we're looking at quite a lot when it comes to algebraic effects. Because what this allows us to say is that no one can handle union find effect in a way that we didn't give him. Right? There is an actual encapsulation of the sorts that abstract types in modules give us, but for the effects. In particular, you might want to say that the I/O is an effect that does not allow its user to handle it. Right? It's an actual effect that we are not allowing to encapsulate in any way. And this does crop up in several places. I think one of Dan Lyon's recent drafts also show the need for this sorts of effects where you don't allow the user to handle the effect. So this is one way to encapsulate this in a sort of a concise and in a way well-founded in a way, right? Because we basically say I/O is a abstract effect. We provide some functions that might raise it. No one can handle it. It will have to float down to the runtime, to the language runtime. And an interesting thing that happens here is that they blur the distinction between effect operations, ask and error, or raise, and the others, and functions. Because they do call an effect, but they do some of their code at the call site, so it's a bit blurry. But on the other hand, function calls can also be thought of as effects themselves. So So maybe they only exposed something that was already there. And well, we could also always expose abstract handling interface in a way. So provide a way to construct your own handler. And in a way, this is sort of similar to views, in that you can provide, just as you can provide an abstract way to view your data type, that might not include all of the constructors that are actually there, you might also think of the abstract effects, or give an abstract effect interface in a similar fashion. So, how do we stand for time? Okay, so we have thought. Oh, frozen. We have thought quite a bit about the meta theory of these abstract effects. In particular, there are some problems in that when we have some effects that are abstract, they might get instantiated to the same effect. And this can lead potentially to problems at runtime. Like these might be abstract names for the same effect. And the effects find their handlers dynamic. So this could lead to problems at runtime. And we have, okay, this is unfrozen. We have thought, oh yeah, so this is an example of such a problem, right? If A, B, and C denote the same runtime effect, so we have function f that has an effect A and C, function g that has an effect B, and we call f, we call g, and then handle with a handler for A and a handler for B. So the whole computation should still have an effect C. Now, if these guys denote the same effect, what can happen is that the resulting code will be pure, and this is just not good, right?
How is the soundness issue if the code is not pure than you expected?
It is an issue if I mean this is just an example.
You have parameters for your effect, so it's just straight up sound, right? Like
Yeah. No, it's just
it's not like you just have
like,
a wrong effect.
if we don't do anything at runtime, this is rubbish, like real rubbish, completely broken. And the way we solve it, very briefly, is that we use coercions. So coercions were used in the realm of algebraic effects in a recent paper at ESOP by Salek and company. But they were used just to ensure that we know how subtyping proceeds in very precise fashion so that our optimizations don't break things. What we do here is, and I won't explain because, like if you want to know a little bit more about what these versions do, just come catch me after the talk. But basically, the coercions that we need to insert here have computational content, so they don't get erased. They don't get. I know how it sounds. It's not as bad as it is. They don't get erased at runtime. They get reified to operations when we erase the types, to operations that basically affect which particular handlers will match which particular instance of the operation. And this is enough to ensure soundness of the calculus. And then there's more things that we did that are sort of weird with respect to what is happening with these sorts of languages recently. So we used to have row polymorphism, but we sort of scrapped it in lieu of implicit monoid structure of the effects, which basically allows us to group effects and treat groups of effects as aliases for another effect. And this is really important if you want to abstract over such groups. Because otherwise, well, you could argue that type synonyms for the effects, you could probably just hack them into the system and everything would still be fine. But when you want to abstract over these, it really becomes necessary to have a sort of sound setup in which to work. So we still insert only one universal quantifier when we infer the types. So in effect, the inference works very much the same way as it did in row homomorphic setting. It's just that the type system at the sort of core calculus level allows us for way more. We don't treat the inference formally for now. It's a thing. It's a work in progress, right? So it's something that we still need to work out. And I think this is true of most of us, that we still have reasonably little understanding of how to program in these systems idiomatically. So what I showed you as an implementation of unification is one way to encode it, but of course there's loads of variations that you could make, and it's not entirely clear at this point, at least not to me, which one is best, if there is. Okay, so that should be it, and if you have any questions, I'd be happy to take them.
I don't see your coercions give you safety.
Come again?
How can your coercions give you fix the soundness problem?
Like this case here, this would lead to a problem if it were type, if it were type safe, as it is. And it's just not. It's like this code without any coercions is not well timed. So you have to insert coercions in order for the code to be well timed, and the coercions are such, like the coercion language is such that if you get a well-typed program, then the coercions that have computational content and will be left after a break. Come again?
Sorry, okay, so the coercions aren't giving you the sound as you have a system that is sound.
Well, I mean, yeah. We wouldn't have a...
Sorry.
Yeah, I mean, yes, so the coercions are part of the type system, and without having something like these coercions, we can have an idea of how to get a system that is sound.
Because they wouldn't work like you had an invariant, anything invariant, any invariant type constructors, you're not going to be able to use the coercions. Like if those were references, if these were rapid references, you're not going to be able to use coercions to fix them back at the end.
Well, so coercions only work on effects, so they don't do anything on types that are different than ours.
Let's take the rest of the
Yeah,
time.
we can talk
show
about
Leo the soundless proof.
Okay.
So I have a small question to Snitchy. You have expert in your group on the coherence of coercions.
Yes.
Have you proved such a result here? Is there like a canonical way to insert that?
No.
It's also about coercions.
Well, this is the technical content of the paper, right? Or a paper that's behind this. So yeah.
Is it fair to say in a system with coercions that your effect annotations are actually a list of effects, and those can only operate in the first element of the list, and to handle something you must first swap it around until it is the first element and then or is there something
It is roughly fair. Yeah, because you can always flatten the list. If it's a monoid, right, then you have a canonical flat representation. So yes, the only reason for the monoid thingy is that when you want to abstract over complex bits, then you need some way of expressing it.
So I'll ask a simple question. What does the slash ABC syntax mean?
I'm sorry, I should have explained it a little bit more. So this is a type and effect syntax. So this is a type of the expression, and this means that there's 3 possible effects that this computation can have, and these effects are abstract. So they are somewhere in our typing context, probably imported from some module, right?
Now that part I gathered. So actually, wasn't clear to me whether that was some kind of
Okay, sorry.
So it's just a way of saying that expression on the
has 3
those possible.
Yeah, those possible.
And with your list of effects,
have you looked at, I know Idris does some things where it labels particular effects so that you can pull them out. Have you looked at other, like you cut other things other than your monoid structure to add, like to collect those effects together and be able to like reorder them? We're thinking of precisely what we want to have as a reordering principle in the future, especially at the surface level. Because at the core calculus level, the monoid with coercions seems to work reasonably fine, but you wouldn't want to write these coercions by hand, and particularly when you have multiple copies of the same effect, which can happen and can have computation, like it can have a sensible meaning to have multiple copies of say writer. Then it's really unwieldy and sort of brittle to have these index into these drivers of effects by hand. So we're thinking of it, and we'll definitely look into the way it brings up.
Here's a stupid question. I mean, abstraction is all very nice, but sometimes you just want to locally define an effect without having to declare a signature. Without giving the user the freedom to provide their own implementation.
All right.
So is there, do these languages have like just anonymous effects where you just locally declare the operation and their interpretations?
So in Helium and in our calculi, language effects are scoped. So you do have a sort of new, in the core calculus you have basically an effect la in E.
And then interpretation.
Come again?
With just one interpretation.
Well, the piping rule says that you have this effect cannot escape the scope. So you can possibly have multiple interpretations within that scope, but once it's out, it's out. And this leads to some other troubles with semantics and stuff, but I believe this is something that you really, really want in a real language. So
I think we'll have to stop here because some of you might want to attend the special keynotes. So let's thank Filip again.